Hey guys, it's your favorite teacher, and we have that quiz tomorrow morning at 8. Don't forget. Okay, we'll see how that goes. And the message that we've been given, by the way, is that we're only going to do things that will improve your mark. But I want you to do the best you can, and I want to give you the highest mark you can get, and I also want you to learn the physics that you need, when you graduate and stuff like that for next year. Okay, so anyway, this problem was, Nick asked about it, so I thought I would mention it here. It says a skier is coasting down a hill that has an angle of 23 degrees to the horizontal. Experiences a force of kinetic friction at the top, magnitude 72 newtons. The skier's speed, is 3.5 meters per second near the top of the slope. Determine the speed after he's traveled 62 meters downhill. All right, so there's a number of things going on. I'm just going to draw a little diagram here. Okay, they give us a lot of information. So first of all, we know that is 23 degrees. Okay. Second of all, we know that this distance down the slope is 62 meters. Okay. And yeah, all right. So and the skier is here at the top. Okay, there's your skier. Okay, so here's the deal. What kind of energy do you have at the top? Well, you have gravitational potential. I'm going to drop a little vertical line here. That's H. Okay, so one of the things you have is EG at the top. Okay, another thing you have at the top is EK, because he has some speed. We know that speed at the top is 3.5 meters per second, right? And we know the formula for EK is 1/2 mv squared. So at the top, he's got those two kinds of energy. Now at the bottom, and we're going to assume that what we mean by the bottom is just relatively speaking, that's as low as he's going to go. So at the bottom, he still has EK, okay? But his EG is 0, okay? At the bottom, relative to the top. You got it? Now what you do here in the middle, he's going to be losing gravitational energy, but also there's work done by friction on his way down the slope, okay? So what you do is the energy at the top will equal the energy at the bottom. If there was no friction, it would be just like that, but then we're going to subtract the work done by friction. So in other words, friction is going to steal some of our joules, right? And so at the top, we have mgh plus 1/2 mv1 squared, like that. Okay, that's what we have at the top. We have the sum of these two things. So that's what goes there. Now at the bottom, you have 1/2 mv1 prime squared, like this. We'll use the prime notation, but it's v2, the final velocity, right? Minus the work done by friction. Now work done by friction is just going to equal the force of friction. We'll use the definition of work times the displacement. Okay, so now if you look at this this data, we've got everything we need. Now we do have to do what we're trying to find. The point of the question is, what is v1 prime at the bottom, right? That's the point. So our goal is to solve for that guy here. I'll use the pretty rainbow one there. Our goal is to solve for v1 prime. All right, so look, now that we've got this, top equals bottom, we have to figure out h. So you guys are experts at trig, right? So this is a right angle triangle, 62 is the hypotenuse, so h will equal 62 times the sine 23. All right, so now we're just going to plug in our numbers. The skier's mass is 61, so it's 61 times 9.8 times 62 times the sine of 23. Plus, there's going to be a lot of numbers here, plus 1/2 times 61 times 3.5 squared, okay, equals 1/2 times 61 times v1 prime squared, like that. And then they tell us the force of friction is 72, so it's going to be minus 72 times, and the distance down the slope, pardon me, the distance down the slope is 62 meters. Sorry, I just lost track of that number. Is 62 meters. Okay, so you have to use, friction works along the hypotenuse here, so it works along that long side. Okay, now I will leave you to finish this off. And there you go. Okay, V1 prime, here, I shouldn't put question mark, I just put blank. So there's only one unknown in there, and that is how you do page 188, number 7. Okay, so that was from page 188 in my lovely handwriting, number 7. All right, guys, see you later.